Well, that's Ladyada.
Hey everybody, welcome to my glowy, colorful desk today. I also got my hair done.
Yeah.
So we're bright and
Sunday night. It's $20 for the seat, but you'll only need the edge.
okay. Let's go for the what? Do you have any news you want to talk about?
Just that this is a big week.
Big week.
Lots of stuff's going on.
Thank
you everyone for your patience with Adabox. As we mentioned, Adabox Classic will be shipping in like month plus-ish, 2 months. And then we immediately end what we called Adabox Classic. And we begin
the next generation.
What we're calling codename Adabox Flow. And the reason is, for people who've tuned into Desk of Ladyada, you know exactly why. But let me explain it.
Okay, why don't you explain it?
For the one person who, it's their first time
hi,
here.
I just showed up.
Is this your first time here? Hi. We go to a singing thing with our daughter and they do that. Anyways, the thing that's going on is you can never get electronic parts ahead of time at a price that you know, delivered when a time that you can expect. So that destroys the idea of a subscription service for electronics.
Yeah.
However, we have a great idea. We figured out a way to solve it. You'll be able to get the latest and greatest Adabox, and we're going to do it in a way that everyone gets a shot. And we're just going to keep the folks that make things not fun out and the folks that make things fun in. That's all I can say. We're going to show our work as we do it, but it's been a challenge. So, Ladyada, let's pretend everything's going to work out and everyone's going to get amazing electronics.
Yeah.
And this video is going to go out. Let's pretend it's all going to work out. What are you doing?
Okay, so let's go to the overhead and we'll show off some stuff we're working on. Okay, so first off, I kind of mentioned this. I spent like 4 weeks going into this tariff swamp. And then like at the end of the 4 weeks, I was like, where am I? And then I had to like hike back. Because people were like, oh, you spent like a month on tariffs. But then like, why did it take you 2 months?
Do you remember when Swamp Thing was briefly licensed and everyone tried to do a Swamp Thing like reboot and it didn't work out?
Swamp Thing's kind of like an intense character.
Yeah. Are you Swamp Thing of tariffs?
Yeah, I'm Swamp Thing. I like merged with, so, you know, I had to like do all the work that I missed. So now I'm getting back into doing hardware. So for like a couple weeks there was like not a lot of, like, I was kind of like, I'm just trying to keep things together.
Yeah. Can I mention one thing?
Yeah, but then I got to do the show.
Yeah. The tariff work that you did, it makes us able to do electronics.
Yeah, I mean, it's not done. I still have to do it.
But you're programming behind the scenes.
We're no longer getting bills that are like 5 digits.
The thing is, everyone, if we were getting an $80,000 tariff bill a day, which
it was
how it started.
Yeah.
Essentially, we'd have to pause Adafruit because we have to stop the bleeding.
Yeah.
And I want everyone to have amazing jobs for the rest of their lives at Adafruit. So we did a bunch of work. We're okay. We're back from the other side.
Yeah.
Yeah. So anyways.
I mean, things could change again. We don't.
Things could change, but Lamar has a bunch of cool electronics, and that solves a lot of things. Buy stuff.
Okay, cool. All right, now let's talk about the electronics.
Yeah.
Okay, so I've been trying to get back to some stuff that was designed a little bit beforehand. So this was actually designed from February, and this is, I'm going to move this out of the way so we can see it. This is the triple output RGB matrix bonnet. Wow, this board is like hot. It's working really hard. So this is an active 3 output RGB matrix driver, and I'll just remove it because actually wait. Let me see if I have. I think I have them. Yeah, wait here. Sorry, let me get one that's assembled but not currently driving stuff. So it's got 3 IDC connectors for Hub 75 or Hub 75E matrices. It has a little slide switch to side, which is the address E. It has an I2C port. I tried to just make it bonnet size. They didn't want to make it like big, so it'll fit on a Pi. Like you could run it on a Pi Zero. You know, the Pi Zero 2, I think would be able to do a couple panels. It's low cost. On the bottom, there are these level shifters, and those convert the 3-volt signal from the Raspberry Pi. Or you could in theory use it with like one of these like Pi Zero like things. They're not Pis, and this allows you to do 3 parallel outputs. And on the Pi 3 and Pi 4, our Pi RGB matrix library that was written by H. Zeller can actually like bit bang. It does like this intense bit banging where it actually bit bangs all the the entire port at once. So you can actually have like all the outputs are pushed at the same time. So you actually do get 3 times the throughput. On the Pi 5, so the Pi 5 is an interesting board because the big change that they made is instead of having, this is a Pi 4. Yeah. On the Pi 4, well, on the Pi 4, you see that there's little helper chips that do things like the Ethernet and the USB. That was replaced, some of it was replaced with the RP1 chip, which was the predecessor to the RP2 microcontroller. And the RP1 chip can do this PCIe to GPIO conversion. So like the GPIO actually doesn't come from the RP5 chip itself, which for all I know doesn't run at 3.3 volt logic. It might have IO coming at 1.8. And then the RP1 actually does the GPIO. So instead of historical chips where you had you literally could memory map into the IO register, just like you do with a microcontroller, and you write the values to it, you can bit bang them out. You can't do that on the RP5 anymore. And so instead, one of the last things Jepler did before he went on his European retirement vacation was he wrote code for the PIO chip on the RP5 to drive matrices. And so if we go to computer, and yeah, so less rainbow. Okay, so this code is in Python and it used PIL to do the drawing, but it uses PIO matter, which is the library that he wrote with multi-lane support in order to use the PIO peripheral, and you write packets to the PIO peripheral that then get output to those RGB matrices. So the nice thing is that you're not using the CPU. You're using this coprocessor, and you just send, I think, 64K packets at a time. I think we actually have to reduce it down to 2K packets, but now that the firmware has been updated, they actually, not like a bug, but everyone was like, why are you pushing 64K packets to the PIO peripheral? And we're like, because we want to drive a lot of LEDs, duh. And they're like, oh, right. So they fixed a bug in the kernel firmware. And then, so we have to actually, one of the things I want to do is retest 64K packet buffers, because right now it says running at like 1 megahertz clock, or 1.2 gigahertz clock, but I think we can drive it much, much faster. Because like I said, you send the packet to the PIO peripheral and then it just like spends its time bit banging all that data out. And, it works really great on the Raspberry Pi 5. It's so nice and solid. And the nice thing is, like, no matter what you're doing with the Pi 5, because it's not using the CPU, you could be like loading web pages or like streaming an MP3 or whatever, or MP4. It doesn't affect the GPIO timing. So that hardware design got done, and that's going to ship out very soon. Okay, so that's lots of glowy. And what's nice is that, this does 3 parallel, and then you could have, fairly large displays. So I actually have 9 matrices, and we might make a little LED wall, like, 3 by 3, which is 192 by 192 pixels. And then because you have a Pi 5 and you have all the CPU time, because you're not using a whole core just to bit bang the GPIO, you could have like video games or something and then downsample them to 192 by 192, which is like not bad, right? Because like most retro games are 240 by 320-ish or so. You could sample it down, and then you can play games or play movies on a matrix. Maybe we'll make that backpack that plays Blade Runner finally, because we need to do that for a while. Okay, so that's number 1. The other thing is we did a lot of little hardware board updates. In fact, I was working on one right now. Close this. So the stepper motor drivers that I did, kind of just because I wanted to have better stepper motor drivers, because all the ones that were on the market were specifically for 3D printers. They were like this kind of standard step stick. And it was like the step stick design was like invented for the A4988 stepper. And then people kept like shoving like bigger and bigger chips into this format. And it's like, well, that's done. Let's make boards that are just for people who want to use the chip, and they're not building a 3D printer. They're doing something else with it. And so we made 2 stepper motor drivers. And actually, they're actually quite popular. People really like these boards, and that's great because they're fairly easy to make and they're easy to support and they work really well. These Trinamic chips I really like. I'm glad I'm finally doing them. And so I wanted to do some more in this family. And the TMC2209 is actually like, well, the A4988 is like the original classic, popular one. This one is great. The TMC2209 is like, it's an amazing driver. It's like super silent. It's really effective. It's got really high torque. But there's a couple other chips that I saw people using. The problem is that I don't know which one. Like, there's like a lot of pros and cons. And a lot of people, when they talk about them, they're talking about them in terms of 3D printers. And again, there might be use cases beyond 3D printers. So this is the TMC2240, which is like it has a little bit more current. One thing I like, it doesn't have current sense resistors. They finally, after the 2209, they're like, maybe we could have like only the internal resistors. And they got them good enough. And so we don't need these big chunky resistors. There are a lot more pins because this one has SPI, but it also has UART. It has both. So this is UART SPI select pin. And you can use SPI or you can use UART. Both have pros and cons. UART is one pin only, but it's like UART. So, whatever, you have to have a hardware pin. SPI is so bog standard. And what's nice is you can run it on any microcontroller or microcomputer. Pardon me. And then has some diagnostics and some sleep modes and encoder inputs and stuff. So, I was just doing the, power section here, this big, chunk of power. And then there's a big ground plane and then the output pins, they have these nice big thick traces because this can do, I think, 2.8 amps, which is a bit, or 3 amps max and 2.2 amp average or something per coil, which is a lot. I had like 36 volts or something too. The next step up from this, I think, is the 5610 or something, or 5160. And that one uses external FETs, and it's not a big deal. You only need like 4 end FETs. But still, it's like, it's more work. But, I will probably make a driver for that because it's like, you have a 10 amp stepper that's going to take off your head. Like, go to town. Okay, so I'm working on that. So I'm going to keep this open. And then I did a couple other, like little breakout boards. I did, people kept like asking me about this chip. And I was like, well, it's not, it's, it's a QT board. This is the STHS34PF80. God, come on, ST, why are you picking? Like, can't you? Letters are free, but still. This is a infrared presence sensor. So it's actually like a PIR sensor, but it's more expensive. Like a PIR sensor is like $2. This is actually like $3 for the chip. So it's not cheap, but you don't need a lens. And it's very small and compact, which I like. I know if people that want to use, millimeter wave, gigahertz wave IR. And I'm like, I'm going to get to that. I said, I have to like, it's a lot of antenna work. But for now, I thought it was like a nice little breakout board. It's I2C, so it's really easy. And then I did also another one. One of the things I do is actually look at what are some like new libraries that people release for like Arduino, and I kind of get like hints of like cool sensors that, again, it's like I can't see everything. And I saw a library for the AS5600, and I was like, this is kind of a cool chip. This is at very low cost. It's like 80 cents, 50 cents or something, magnetic angle sensor, and it comes in a SOIC8. You have the magnet on the top or the bottom, and as the magnet rotates, it's a potentiometer, and it can do, it actually has 2 modes, which I like. PWM output, which is like a little hard to use, but maybe if you have a chip that has a timer, that's kind of nice. And it has, you can PWM it. Sorry, you can RC filter it, the PWM, and get analog output, and then you can read that with an analog input. Just make sure you use a good filter that is well below the frequency. Or you can use I2C, and you get that you can make little potentiometers that are you never have to worry about centering or zeroing or mechanical damage to them, because potentiometers they do eventually flake off. And so do rotary encoders. So this is magnetic rotation sensor. You can also use it as a rotary encoder because it goes all the way around. Actually, it's another thing about it. Unlike a potentiometer, it goes 360, right? It doesn't stop at 270. I think that's it. Also, this OLED bonnet. Okay. And then the big thing that I worked on. So let me gently move this out of the way. Thank you. Is I did a bunch of work on fruit jam. Actually, I did a bunch of work a couple weeks in a row. And I finished the hardware bring up. Go to the overhead. I finished the hardware bring up for Rev B, which means that all of the hardware.
Yeah, we'll have the final prototype this week.
Yeah, hopefully.
We're sending one out to a friend who's a writer, and they're going to do a review.
Yeah, I mean, we have some code that, you know, some of the projects we've done for the Metro could also run on the Fruit Jam. So, you know, hopefully we'll be able to get those working. You know, as you know, some of the things were easy, like the USB, you know, that was from Rev A, but the stuff that I added for the ESP32-C6 to add a Wi-Fi coprocessor, or, you know, you can also do BLE. This chip, it was like a little annoying because I've never used the C6 as a coprocessor. We have a fork of the Airlift firmware that runs on it, and it's a great low-cost chip. It's like, you know, it's $1, $2 or something, and it can do, you know, wireless, and it has SPI, and it's good enough to do 2.4 gigahertz Wi-Fi, and it's like it's a modern chip, and it you can go to deep sleep mode and stuff. So I just had to uncap it because I had to actually have access to I forgot that there's the strapping pins on the ESP. It's like they will drive you crazy until you realize what they are, because a lot of pins they're accessible, but you can't use them. And some pins are accessible and usable, but you're supposed to like strap them low or high. And the module sometimes straps them for you and sometimes it doesn't. So GPIO 8, you have to pull down if you want to do UART bootloading. And the way that I load the firmware onto this chip is I use the UART on here. So this is a USB to UART converter, and then I use that to load the firmware because I don't want to like expose the pins, and that way it's like the chip it can do the programming for you, which is great. But unlike other chips which I've used before, I didn't realize that you have to like pull D8 low. And the reason I didn't realize that is because when you do USB bootloading to the C6, you don't need to. You only need to do it if you do UART bootloading. Why, I don't know, but like it's I had to revise it to get that working. I had to pop the cap off because the D8 pin was underneath, right? It's underneath the module. You can't get to it. It's not like a castellated. It's an underneath pad. So, this little red wire is just soldered carefully to the D8 pin and then to ground. And then I had a couple other mistakes and stuff. But I think Rev C is going to be the final Rev. And I'll show real quickly, and then we'll go to the great search. So you can go to the computer. Also show the front plate. So the final design.
Huh? Or do you want to stay on the?
No, the computer. Yeah. So now that all the hardware's been tested, and I also had to revise a lot of the libraries because one thing I learned as I was doing this is that a lot of the libraries that we've written for the art. So the thing that's cool about the Fruit Jam is it uses like all the PIOs, right? Because it uses one PIO for I2S, it uses one PIO for USB host, and it uses it doesn't use a PIO for DVI, but it can use one PIO for NeoPixels. And then it has 3 PIO. And then, if you want, like the NeoPixels, you don't have to use PIO if you don't want. And then you can, you have one for like some other, whatever other weird bitbank thing you want to do. But as I was working on this, managing the PIOs, you have to allocate them correctly. Like historically, you would just like pick a PIO and be like, I'm using PIO 0. But now you actually have to be a little careful because depending on how you don't always know which PIO is going to be available. And so the SDK updated to now let you, there's this new function which I really dig called get the PIO and state machine and just leave me alone. And I'll show it. It's under, I did a PR to the NeoPixel library because I kept bumping, it kept like crashing and colliding into whatever I was using with USB, and I didn't want to have to do this thing where it's like, okay, USB, and then like you tell it what PIO you want to use. So, find the function because this was, and then, I was talking to somebody else and was like, use this function because it kind of like solves a lot of problem. It was, yeah, so it used to be like you would like, let me see where the code is removed. Okay, so the new function is called PIO claim free state machine and add program for GPIO range. This handles GPIO larger than 32. It gets you the right PIO and it gets you the thing that can fit, like it gets you a PIO and state machine ready to go. The old code, you would request the state machine and then you would separately, I don't know if I can find it. Yeah, you had to do like add program separately from like claiming it. And it just you had to claim the unused and claim state machine. And it just got and you'd have to do it for PIO 0 and then try PIO 1. But it's like, they're probably going to come up with more chips that have more PIOs. So, this function call is kind of the better way of doing it. Because that way you just get whatever is available. And so that let me actually start to like test everything at once. So now I've got, the only thing that I did bump into, I have to figure out is the NeoPixels. They use a PIO, but the PIO is blocking. And NeoPixelate has non-blocking, but it uses an IRQ, and the IRQ collides with the DVI. And so right now you can use NeoPixels, but you can't update them constantly because it'll freak out the DVI. Like you'll block the chip, and the DVI is running on the same core. Now, in theory, it could run on a separate core, but like I2S might be, I don't know. So I'm gonna figure this out, but it does work. And then, I fixed the D8 issue with here. And then Mr. Ladyada wanted infrared input, so I added that. Scott wanted me to move the HDMI out here, DVI output here, and the headphone jack. So this all got moved. And so I think that the hardware is actually done with Rev-C. I think like all things are functional. They definitely don't work in CircuitPython, but I also have to make sure they worked in Arduino. And they're also I'm going to write some demos in Pico SDK that use all of this hardware as well. So it'll be interesting. And then this is the front plate. So this plate will fit on top. And it will protect the components. And I designed it so that like the buttons are really long and the header's really long and the switch is long to stack above. So you'll have like it'll be like a nice little sandwich. I like these little PCB sandwiches. A lot of the designs I'm doing now are like 2 or 3 layer sandwiches. And it's like, yes, we can design cases and we probably will have a 3D printed case and stuff, but there's not enough demand for this to do an injection molded, like 10,000, 50,000 piece run. So like for the low cost of a PCB, which is like $2, you get a nice front plate and it's nice and protected. Like it's not protected from the sides, but it's like, it's at least not like this thing you could immediately spill your Coke on. Okay, how are we doing on time?
We're doing good. You're up to 23 minutes.
Okay, great. Let's do a fast-paced great search.
Okay, let's go. Great search.
Where in the world is that part I need? The great search with DigiKey.
All right, everybody, it's great search. Everybody's skill, big later, easier, power, lady. What's great search?
Okay, so we just say speed 1. So we're doing this triple output RG matrix active bonnet, which I designed and I was just showing it off. It looks like this, and it has a 3 to 5 volt level shifters on the back as output to drive the Hub 75 matrices. They want 5 volt power and they really want 5 volt logic too. Even though they don't need to and some work without it, I found that 5 volt is the best way to go. So this does active level shifting. And to do that, we need to shift a lot of pins from 3 volts to output. And it turns out to be like 8, 16, 24, 25, 26, a lot. And I want to use an 8-pin level shifter, and I want it to be able to handle 10 megahertz or higher. That's important. Like I don't want a slow chip. And the most important thing is it takes 3 volt logic in, but outputs 5 volts. So you power it from 5 volts. That's how you normally do this. Sometimes you have 2 outputs selections, but basically just make sure that it can handle 3 volts input safely, output it to a clean 5 volts and do it quickly and be small. I want it to be like, HTSOP or HSOP, not SOIC and definitely not DIP, right? I want it surface mount, small, compact, easy for me to place. and inexpensive because I need 4 of these, right? I need 4 of them. And if they're like 50 cents a piece, like suddenly I'm paying $2 for level shifting. I don't want to do that. I want to pay like less than $1 for all of them, less than 50 cents for all of them. So let's go to DigiKey and see what we got. Okay, so we want, these are actually called buffers. So there's non-inverting and inverting buffers, but they're all kind of in that same buffer, driver, receiver category, things that take like one signal and convert them to another one. So as usual, we're going to look for active only. And let's do stuff that's like normally stocking. And we're going to exclude marketplace products just to keep it a little bit more organized. Marketplace usually duplicates of stuff. And this is a common item. I'm expecting DigiKey to stock this. Now there's one thing that's a little bit tricky here, which is number of elements. Now remember, I want as many as possible. And in general, logic either comes in 1, 2, 4, or 8. You can do others, but it's usually like the cost gets a little bit expensive. So I want 1 and 8 here, and I want 1 and 8 here. Why? Because it could, the way that they might consider it like 1 bus times 8 pins, or they might say like, well, it's 8 pins and like each one has an output enable or something. I don't know. So I just want to make sure that there's like 8-ish of 8-ish. Okay, I still got these 1s. Unfortunately, there's no way to say like, well, I only want one or the other. But if I look at the ones that do have like the more pins, and that's another thing is I can filter out all the SOT23s, because anything that's less than, I know anything less than 16 pins isn't going to be a valid chip. So I'm going to pick only the 20 because I need at least 8 in and 8 out, and then power and ground. Okay, so like at least 18 pins, so 20 to 24 pins. These will never have enough pins, and that really helps me filter out all those individual items. Now we're getting to, these are looking good. Lots of pins, and they're like non-inverting, inverting. So let's look at those inverting and non-inverting. So there might be situations where you want to invert the signal as you buffer it. We don't want to, so we're going to pick non-inverting. Transceivers go both direction, which I don't care about. That's not unusual, but like I can always just set the direction. I only want it to be outputs, not a big deal. And then I don't want open collect or open drain. I need it to be push-pull. Tri-state's fine. There's an output enable. That's okay. And then, okay, so now we're looking pretty good. So now we have to look at the voltage supply. Now remember, I want a level shift from 3 volts up to 5, which means that I need to have the power supply be at least 5 volts. And so I'm going to go through and like I'm holding control, and I'm picking only the ones that cover 5 volts. So like I'm skipping the 1.6 to 3.6 because that's not going to be able to give me a 5-volt signal. Okay, cool. So this is looking pretty good. Next up, I could filter out and say I don't want SOPs or dips. I only want surface mount. That gets rid of another 50. One thing about looking for a logic level is you're going to see that there is a lot of options, that's kind of generic. So you'll see many companies come up with very similar chips. Another thing is I don't want SOICs because they're going to be way too big. So let me just pick off, I'm going to just skip, I'll take the QFNs, but I'm going to skip the SOICs. That gives me, a slightly smaller number. That way I don't accidentally get one that's bigger. Another thing that, if you guys saw on the package and case is that SOPs, TSOPs come in different widths, and this like really bites me. Sometimes you have to really watch out. Some are skinnier and wider. You can have a footprint that supports both. You just have to have like really long little tails, pads on your footprint, but just watch out because I have many times I remember once like the extra wider ones instead of the narrow ones. And then from then on, I'd redesign the board or maybe I return them. But from then on, I just used the footprint that was the wide one and had support for you could put the narrow ones down and it would just be they'd be kind of sitting there floating in this wide pad. Okay, so now we've got lots of options. So the only thing is that none of them really tell you are they level shifty. Now, if you knew your 74HC logic type, you could pick those out. But instead, what I'm going to do is, pricing was important. So I'm going to just say, because I need 4 on each board, and I make about 250 pieces on my first run. So let's just make sure that, I'll start at the top and I'll see which ones are available. And different series will tell me VHC or VHCT. So let's look at, let's say I don't know each one. But you do want to read the description, and they'll tell you some things. And one thing that was interesting is they said here, they're like, no, you can see this came later, because I guess people used it the wrong way. They said there's a diode between the bus and VCC terminals. And so you can't use this for 5-volt and 3-volt systems. Like you can't mix and match them. Could you make it work? I don't know, maybe, but I'm going to just say like, hey, skip it, because I don't want to, if it's giving me a warning, it's like going to be more work than it's worth. And then, so we can go to the next one, AHCT. And this one is a transceiver, synchronous two-way communication, runs from 4 to 5 volts. And then, they show you the direction. They go each way. And there's output enable. It has a kind of a standard pinout, comes in a lot of different packages. And then, so we want to make sure that the input voltage range is compatible with 3.3 volt logic. So we go down to the recommended operating conditions, and they're like, look, you have to power from 5 volts, and that's like, cool, no problem. The input high voltage is 2, which is good, because if it said input high voltage is 3.5, which sometimes it does, that's not necessarily going to work with 3.3 volt logic. It might not work, because they're saying, look, your input voltage has to be at least 3.5, but your 3.3 volt logic, sometimes the logic might trigger a little earlier, but for the most part, you need to make sure that the signal coming in is higher on the high level than the high level input and lower than the low voltage. So this one will work because the input is 3.3 volts higher than 2, and the low input is going to be 0. It's lower than 0.8. And then you could have up to 5.5, but so this actually can, this can shift from, this won't work with 1.8 volt logic, but it will work for 3.3. It will work for 3 logic and maybe 2.8 volt logic too. And then the last thing we want to just check real fast is, is the speed. Now, sometimes this doesn't really matter, but I do know that I'm going to have at least 10 megahertz signals coming through. So let's check, I'm going to assume that we're running it like your standard, non-industrial, you're up to 85 degrees C. Temperature, let's say, gets nice and warm. I don't care about OE because the output enable is always going to be on. I care about signal, like how long does it take to move the signal from one side to the other? And there's different capacitances. Let's say we have high capacitances. We have this long cable. So at worst, it's going to be, 11 nanoseconds. It's 10 nanoseconds. Let's say 10 nanoseconds. So we say, 10 times, let's just do the nanoseconds. So it's 1 divided by 2. 1, 2, 3, 1, 2, 3, 1, 2, 3. That's a nanosecond times 10 nanoseconds. Invert it, 100 megahertz. So divide by 2 because you have to go up and down. So 50 megahertz is, the, what's it called? The transport. And hold on, there's a word for it. Propagation, right? The P is propagation from low to high or high to low. So way more than the 10 megahertz that I need. So I know I'm good to go. So this chip will work just fine. It's like the lowest cost one, but if you're willing to pay a couple more cents, some of these have tariffs, just watch out. That could be 10%, so that can increase your cost, but this one is tariff free. So you can pick this one. But here's the good news. Now that you've checked the data sheet, check the data sheets for other alternatives just in case. But 99.9% of the time, if one of these A74 AHCT 245s will work, the entire family will work because all of them have the same specifications. And then the SN is just like TI's prefix, and the DGSR is the packaging suffix. So the core name for that logic is the 74 AHC 245. This will work great as an 8-bit logic level shifter from 3 to 5 volts.
All right, and that is the research.
Where in the world is that part I need? The Great Search with DigiKey.
Ladyada, that is
That was a big show. Okay.
the desk of Ladyada this week.
A lot's happening. Get right back into work. Well, I have some childcare, and then
Yeah, and let me just do a shout out.
Okay.
I'm going to try to remember to do a shout out at the end of the desk of Ladyada's.
Okay.
So in our household, there are so many things that are important now, like goldfish crackers,
Stone Temple Pilots.
like the entire catalog of Stone Temple Pilots that I listen to because there's this AI thing that you can ask. I'm like, give me every song that mentions Star Trek. And there was a song that he did that mentioned Deep Space Nine. Anyways, there's so many things that run this household, and I took it for granted, one of them. And I'm so happy. I'm so happy that I get to do a blog post later today
Okay.
because I want to do like a shout out on Desk of Ladyada on
Yeah.
like, oh, what other like cool people did something at their desk over the weekend.
Yeah.
And I was thinking about Margaret Rudkin, founded Petridge Farms, sold it to Campbell Soup in the 60s. She made Milano cookies and goldfish crackers.
Okay.
And you know what she said? There's no job that a man can do that a woman can't do too. She was a pioneer. She was the first female board member at Campbell Soup. She was going around looking for a special wheat to give her son because he had like a gluten thing. And then she went on the Queen Mary and she went around the world looking for like cookie taste that Americans would like. And that's how this all came about. And the reason I'm saying this is because I have to order Milano cookies and goldfish.
Thanks for watching, everybody.
Very strong woman leader who
Yeah.
made stuff, right?
And those are tasty cookies.
Right?
A lot of cookies are tasty.
Aren't they? The new mint ones are pretty good.
Yeah.
Okay, that's your Desk of Ladyada and Fact of the Week. It's Founder of the Week. I want to have a founder story on Desk of Ladyada each week. Bye.
Bye.